Hello and good afternoon, friends. Welcome to the CEC EduSet live lectures. Through previous lectures, we try to understand about the quantum mechanics, the various aspects of this very concept. We try to understand in this very lectures of ours, which held the previous 2 days. Now we are going to discuss more about what quantum mechanics is. That is through postulates which we have left in the previous lecture, and today also we are proceeding from the postulates portion only, and we are going to learn more aspects of this very topic. And for this we have again with us in our studio Professor Rita Kakkar, who has given her immense contribution, that is of almost 30 years, and in the field of the subject, that is in the fields of academics. She is again with us in our studio, and she is going to throw more light on this very topic, that is quantum mechanics. First of all, I would like to welcome our guest, Professor Rita Kakkar. Hello ma'am, welcome to the EduSet lecture. And I think we are going to start slightly from the point where we left yesterday.
Okay, hello again viewers. I'll briefly, because we were interrupted a lot during the postulates, I'll briefly again talk about the postulates and a little about the uncertainty principle, the quantum mechanical aspect. And I have, in fact, in the first lecture I had said that I will do particle in a box problem in some detail, but listening to the your queries, I have realized that many of you are more interested in atomic structure. So I have rethought about the lecture. I am going to talk about atomic theory, a little bit of about the atomic theory. Now coming to the postulates, I have rephrased them in a simpler form. The first postulate, as you remember, concerned the wave function. The state of a dynamical system of n particles is described as fully as possible by an appropriate state function psi, which is a function of q1, q2. All these q's are the position coordinates, and as I said, if there are n atoms, there will be 3n position coordinates, because we are talking in 3-dimensional space, and the time. This is a function of all the 3n coordinates of the system and the time and the n spin coordinates that we will not talk about right now. Then the state function psi has the property that psi star psi d tau is the probability of finding particle 1 between q1 and q1 plus dq1, and so on. And since psi star psi, the important thing is that since psi star psi, I told you that when you write a star, it is the complex conjugate where iota in the wave function is replaced by minus iota if it is a complex wave function. It represents a probability, and the probability that the particle is somewhere is unity. If you talk about probabilities, you know that the total probability of an event is always equal to 1. That means if you integrate psi star psi, which represents the probability density, into the volume element, you get a probability, and the sum total of all probabilities should equal 1, and d tau is the volume element. And there is a corollary that psi must be well behaved, that is, it must be single valued. I have given you the reasons for all that. Finite and continuous for all values of the position. It should not become infinite, because probability cannot be infinite anywhere. It should be well bounded. At the boundaries, it should become equal to 0. And now we come to the second postulate. The wave function that represents the state of the system changes in time according to the time dependent Schrodinger equation, and here I have put arrows over q and p to signify that they are vector quantities. You could write them as bold also, and this is the time dependent Schrodinger equation, which we have already discussed, where h is called the Hamiltonian operator and is a function of position, the momentum and the time. The third postulate was that for every observable property of a system, there exists a corresponding linear Hermitian operator, and the physical properties of the observable can be inferred from the mathematical properties of the associated operator. Here we are connecting experiment to theory. Then we come to the fourth postulate, that suppose that A is a linear Hermitian operator corresponding to an observable, and there is a set of identical systems in the state psi, which is an eigenfunction of A, that is A psi is equal to small a psi, where A is a real number. Then if an experimentalist makes a series of measurements of the quantity corresponding to A on different members of the set, he or she will always get the same result, small a. It is only when psi and A satisfy the eigenvalue equation, that an experiment will give the same result on each measurement. And the fifth postulate concerned that given an operator and a set of identical systems characterized by a function psi that is not an eigenfunction of A, a series of measurements of the property corresponding to A on different members of the set will not give the same result. Rather, a distribution of results will be obtained, the average of which will be given by this mean value theorem, this ratio that I have written. This is the so-called mean value theorem. If the size are normalized, the denominator becomes unity, because we have said that the total probability should be equal to 1. We normalize the wave function by multiplying by a constant, so that the psi star psi becomes equal to, when it is integrated, becomes equal to 1. There is also a sixth postulate that the total wave function must be antisymmetric with respect to the interchange of all coordinates of one fermion with those of another. Here I will try to explain what a fermion is. Electrons, if you remember, have an half integral spin. S is equal to half, and that anything which has an half integral spin, it is called a fermion. Whereas anything where S is equal to 0 or 1, where it is a full integer, it is called a boson. And this name boson comes from Bose, a very eminent Indian scientist, a physicist from India, who gave Bose-Einstein statistics. He collaborated with Einstein and gave Bose-Einstein statistics. And anything which has an integral spin, for example a photon has a spin of 1 unit, so it is a boson, and an electron is a fermion. A proton is also a fermion, but a photon is a boson. These coordinates must include the electron spin. That means if you interchange, if you have the hydrogen molecule, then if you interchange the two atoms, hydrogen A with hydrogen B, then their interchange should always give you, and the sign of the wave function must change. This actually the Pauli exclusion principle that you learnt about, that all the 4 quantum numbers cannot be different, cannot be the same, is a result of this antisymmetry principle. I think we will not be able to discuss this in any detail, and then we have commutators, so on. That I just want to say one thing, that two operators, if the multiplication of an operator with another one means that you first carry out an operation with one operator and then with the other one. For example, if you have two operators on the top, you will see q, r, psi, that r first operates on the wave function psi, and then the result is operated upon by the q operator. That is one result. When q, you operate with q first, and then with r you write it down as rq psi. Q, because it is closer to psi, the first time you will operate with q and then with r. In general, it is only in very certain cases that the result will be the same. In most cases the result will be different. When the result is different, we say that the two operators do not commute with each other. If the result is the same, we say they commute with each other. So the commutator of an operator QR is QR minus RQ. That means if you interchange the order in which the two operations are carried out, then the difference between the two results is given by QR minus RQ, and we call it the commutator. Now commuting operators have a very important property, that in that case the eigenfunctions of one are also the eigenfunctions of the other one, and that means according to our third postulate, if you have eigenfunctions you can be certain about the result. That means these two properties can be simultaneously determined. In case they do not commute, in that case you cannot determine, because the eigenfunctions of one operator need not be the eigenfunctions of the other operator. That means if you have determined one property exactly, the other one will not be determined. And x and px are two operators which do not commute with each other. The commutator is equal to iota into h cross. What this means is that if you can determine the position exactly, you cannot determine the momentum exactly, and there is an uncertainty about them. So the uncertainty relation is also a consequence of the commutation of the two operators. The energy and the momentum, kinetic energy and the momentum commute with each other. That means if you know the momentum, you can find out the kinetic energy, because the kinetic energy is equal to p square by 2m. and I've already told you that there is an uncertainty delta x and delta px, and when you multiply them by each other, what the Heisenberg uncertainty principle tells you is that the product will always be greater than or equal to h cross by 2. The minimum uncertainty in these measurements is h cross by 2. That means if delta x is equal to 0, if you have determined the position exactly, delta px will be infinite to make the uncertainty product greater than or equal to h cross by 2. So, any two such operators which do not commute with each other, there will be an uncertainty. And what this means is that suppose you have a classical particle, you can label it, you can say I am a classical particle, my position is this one, my momentum is this, you can determine both of them exactly. Whereas for a quantum mechanical particle, you can only talk about probabilities. You can say it can probably be here, it can with this probability, it can be here, with this lesser probability, it can be in the yellow region, and it has a maximum probability here, plus we don't even know the momentum exactly. So now we can show this, we can show formally that delta x into delta px is greater than or equal to h cross by 2. Similarly for the y variable and the momentum in the y direction, but this does not apply to the position uncertainty in the position in the x direction and the momentum in the y direction. It can be equal to 0, it need not be equal to 0 also, because these two operators will commute with each other, because one contains dy dy and the other one contains x, so there is no reason that they should not commute with each other. As we talked about x and px, there are two other, we call such variables as conjugate variables. X and px are conjugate variables. Similarly, the energy and time also obey an uncertainty relation, which you probably are probably not aware of. The other uncertainty relationship you have already learnt about. Now, the consequence of this is that energy and time. Suppose your particle is in the lowest, the ground state as it is called, n is equal to 1 level. Now, because you cannot, there is no energy level lower than n is equal to 1, so there is no way that it can lose energy and go to a lower state. To take it to the second energy level, which is higher in energy, you require to pump in energy to the system. That means if it is not being acted by external forces, the particle will remain in the n is equal to 1 level forever. That means that the uncertainty in the time is infinite. It will remain there forever until you disturb it. And this means there is no uncertainty in the first energy level. But for the second and third energy levels, there is an uncertainty, because they can always lose a photon and go down to the ground state, or they can lose energy in the form of heat and go down to the ground state. So that means delta t is not infinite. So delta E is also finite, delta t is also finite. So there is an uncertainty in the energy levels. How do we know this? When we take, if you have studied spectroscopy, we can know that whatever we are learning about in quantum, we can confirm that it is correct by doing a spectroscopic analysis. So in electronic spectroscopy, an electron will go from, say, the n is equal to 1 energy level to the n is equal to 2 energy level with absorption of radiation, and you can have a spectrophotometer which can detect where there is absorption of radiation. Now, suppose the first and second level, they were exact, there would be absorption of only one energy level corresponding to the difference in energy between the n is equal to 1 level and the n is equal to 2 level. But what you see is a distribution of frequencies with some width of the spectral line. This means that the energy level of the higher energy level is not certain. It can vary between the highest peak and a little to the left and a little more to the right. So this is a confirmation that the Heisenberg uncertainty principle operates for energy, and the energy, if you know, is equal to h into nu. So if there is an uncertainty in the energy, there is also an uncertainty in the frequency, which is given by h into delta nu. So you see that the intensity versus the frequency gives you a peak instead of gives a broad peak instead of a single line, which you would have expected if the n is equal to 1 and n is equal to 2 levels were both exact. But n is equal to 2 level is not exact, and that is why there is an uncertainty, and the lifetime of the excited state is normally of the order of 10 raised power of minus 8 second. Now I have in my very first lecture I said I will take you through the exact solution of the particle in a box, because that is one problem that can be solved exactly, does not involve too much maths, but I realized from your questions two things, that there are students with widely varying interests. On one hand, I got questions like what is kinetic energy, what is an atom, and so on, and on the other hand somebody asked me about Hermitian operators. But that means that the level of students is different. There are some of you who are yet in school, some of you who may be doing MSc, because there was a caller who was doing MSc. So in this lecture I will try to keep it to a middle level, and you can send your queries to the channel and you can ask them in future what kind of lectures you want for whatever level, because but today I'll keep it a little at a middle level. So one question that was asked is what is classical mechanics. I'll show you with the help of the graphic here. You've seen ramps. When anywhere you see that scooters and all, for them you have a ramp because they cannot go down the stairs. So I've shown you a ramp on the left, and this is where you can walk on the ramp with any size of your step. You can take a small step, you can take a large step, and as you are going up, your potential energy is increasing. Your potential energy can increase continuously because you can take small steps, you can take large steps, you can take whatever size step you want. But suppose you are going up a staircase, then you can only vary your energy in steps according to the size of the steps. This is the difference between classical theory and quantum theory. Classical mechanics is all the mechanics that was known up till the 19th century, and nothing, this quantum mechanics came in 20th century because for smaller particles it was becoming difficult to explain some phenomena regarding light, regarding the properties of atoms and so on. So classical mechanics is like a ramp where the energy is continuously changing, and quantum mechanics is where the energy can only change in steps like this. Now there is a correspondence principle which says that if you have large particles in large containers, in that case quantum mechanics and classical mechanics gives you the same result, because the step size becomes very small, and that means it is almost like continuous steps, and that is why for something like an atom or a molecule or anything you can use quantum mechanics, but for balls and so on you need not use quantum mechanics, you can use classical mechanics, which is much simpler to adopt. So you know what kind of properties you can do with classical mechanics and what kind of properties you can do with quantum mechanics, and I hope you understand the classical mechanics.
Hope students are listening to us and they are getting the information, and as ma'am said, she tried to solve your queries, and one student asked about the atoms yesterday, and I hope the student might have got his answer, and I hope today also we'll get the calls, and it is a humble request, please ask questions related to the topic only. Yes ma'am.
Yeah, so now I've already discussed the uncertainty principle. I'll move over to the hydrogen atom. Now hydrogen atom, I will not start straight away. I will show you the atomic models. You can imagine, years ago how people thought how there can be an atom. Now this is the Bohr model. Inside an atom, he assumed that there was a nucleus. In the center you see a nucleus, and there were electrons orbiting, because I remember a caller asked what is an orbit. An orbit is a fixed trajectory where something is moving in a fixed orbit around the nucleus, only at a particular radius around the nucleus. Now I've already told you, I think, that according to Bohr's model, these electrons were stable only when they were at a fixed radius from the nucleus at those particular radii, they were stable, because there was a question at that time, how can the electron be stable when it is orbiting around the nucleus? Because something that a charged particle, electron has a negative charge, when it is orbiting around the nucleus, so it is losing electromagnetic radiation, it will ultimately fall into the nucleus, so the atom cannot be stable. But the atom is stable, and Bohr said only when its angular momentum is quantized, that means that it has a particular value of a radius, which there are many allowed values of the radii, but only at those particular levels will it be stable. Now, going far back, we are talking about 400 BC, that is, we are in the 2014, that means 2400 years ago. What happened? They assumed that it was like a ball, a billiard ball, and round and so on. In fact, at that time they thought that every element, because they knew that every element had different properties, they assumed that any molecule or anything which tasted bitter was, which had spikes, or some atoms were like cubes and so on. But this is, now I've shown you some pictures of some of the players who were around, who helped us understand this. Democritus at the top, we have Thomson, we have all the people, Lewis, all these pictures. And I'll start with Democritus. Normally it is believed that in 400 BC, 400 years before Christ, and that is 2400 years ago, Democritus was a Greek scientist. Now, the Greek people were thinkers, they never did any experiment. So, what he thought, he think about, why I always try to explain history, because it is very important to understand the scientific mind. What went on in their minds? They never did any experiment, they never tried to find out the structure of an atom, but what they thought was, suppose you take a block of any metal and keep on breaking it into pieces, there will come a time when you cannot break it any further. So, this is what he thought, that there must come a time when you cannot even break it further, because it becomes indivisible after that. And so he called it atomos, and the name stuck. In Hindi we call it anu. So atom is the same thing, the smallest unit which cannot be broken. Today we know that this is wrong, because an atom has electrons, it has nuclei, so you can break an atom into all this, but atomos means that something that cannot be cut, जो काटा नहीं जा सकता, तो it cannot be smaller than that. But we know it is wrong. But think how, 2400 years ago is a long time ago, when they did not have any sophisticated instruments. This is what he thought, that they were vibrating. They knew then that these atoms were vibrating about their positions. They were small and hard particles made of the same material, but they thought that different elements, because they had different properties, the sizes must be different, the shapes must be different. I told you, they thought that some of them were cubes and some of them had spikes coming out, because they thought that something is bitter, karva hai, so it must be, pointed and like that. But they thought that they were infinite in number, you can have any number of atoms, and they were able to move and join together, making molecules. Now, for 2000 years, nobody even thought about this theory, because the reason was, because at that time there were other Greek scientists, Aristotle and Plato, who thought that the four elements, earth, fire, air and water, they formed all matter. Jaise we call it Panch Tattva, they were talking about four of these, and they thought, and they were absolutely wrong, because this is not true, but they were more known scientists, so people believed them, and so that is why for 2000 long years nobody even thought about it. And now I'll tell you something interesting. Our own Acharya Kannad, whenever we go back to history, we find that there was some Indian in India, they already knew about this, and he knew even much more than what Democritus had done. But the Western world always credits Democritus and the people after him, Dalton and so on, with the discovery of the atom. We had an Acharya Kannad who said every object of creation is made of atoms which in turn connect with each other to form molecules. See how close it is to the modern atomic theory. He said that there are what he called anu, or matlab, they can join together to form molecules. We know that this is what happens, bonding is like that, and he was the one who brought about the atomic theory. For the first time ever in the world, 2500 years before John Dalton, but we always say that Dalton was the father of atomic theory. It was Acharya Kannad. Also described the dimension and motion of atoms and the chemical interactions with each other. He had studied a lot of chemistry, and he even knew how they interacted, how they formed molecules. In any subject, whenever you go down actually to history, you will find that India was far ahead of other people. Now the timeline I'll just show that Aristotle's 4 elements was in 400 BC, and then I told you that nobody even thought about Democritus's theory. Then came the Dalton model in 1803, then the Thomson model. Very quickly I'll tell you, Dalton said that every element is composed of atoms, and then these atoms combine together in small proportions to form molecules, and this is, I think, your first point when you start studying chemistry. The Thomson model was, Thomson discovered the electron in cathode ray tubes, and he realized that atoms were not indivisible, you could break them into electrons. Rutherford then did his alpha particle experiment, where he bombarded a gold foil so thin that it was just an atom thick with alpha particles. Alpha particles are helium nuclei. That is, the helium nucleus, without helium, you know, has an atomic number of 2, so it has 2 protons and 2 electrons. When you remove the 2 electrons, it is left with a charge of +2. Now he found that when he bombarded the atoms with the gold atoms with the alpha particles, most of them just went through. That means that most of the space was empty. It was vacuum that it was passing through, but many of them were deflected even back. This meant that there was something very, very dense inside the atom, which we now know is a nucleus, which has a positive charge because it was repelling the positively charged alpha particles. And then the first major model that we had was the Bohr model, and Bohr model came in 1922. So this is a timeline of 2500 years, and Bohr model said that an atom could be stable. The Rutherford model had one problem, that they were not able to explain why the atom was stable if it was orbiting around a stationary nucleus. Bohr model I've already explained, and now we have the modern theory of the atom, which is the wave model. Now in the Dalton model, it was in 1800, he was an English chemist. He performed a number of experiments that made him understand that there were atoms. He said that, I've already, I think, said this, that all elements are composed of atoms and they are indivisible. So till then they thought atoms cannot be broken up and you cannot destroy them. They of the same element are exactly alike. Until now they thought that all elements have the same material, but now he said that of the same element they are exactly alike, but different elements are different, and compounds are formed when they combine in small ratios. Now this is the theory that became the foundation of modern chemistry. Then came the Thomson's plum pudding model, where Thomson, if you remember, was the one who discovered the electron, and he thought it is like a plum pudding. You know, plums, like you make a cake where plums are distributed evenly in the cake. So he said electrons, there is a positive charge which is spread all over. He never talked about the nucleus, and the electrons are equal to the positive charge. There are negatively charged electrons, so that the atom is electrically neutral, and they are distributed everywhere inside the positive charge. But something like this, the electrons are in this is a cake, a kind of pudding where the electrons, raisins, kishmish dalte or something, that they are distributed, something like that. And but we know, and how did he know? Because he had studied the cathode ray tubes which used to be in the earlier TVs, the cathode ray tubes. There are, and he was able to find that there were some negatively charged particles because they were repelled by negative charge. And I think I'll quickly go over the important fact that Thomson found was that atoms are divisible. You cannot say that atom is indivisible as they were thinking. Then I've already told you about Rutherford's gold foil experiment. I'll quickly go through this because many of you have already studied this, and I've already explained all this. So I just want you to see the pictures to see what kind of experiment he had done. Most of them just went through. How did he know? That he put a zinc sulfide screen where scintillations, the shiny, he was able to see that the alpha particles were striking that screen, which was made of zinc sulfide. And so he decided that most of it was empty space, and the centers were very concentrated, and they were positively charged because they repelled the the alpha particles. And so this is how he made a model where he had a nucleus, but the electrons were uniformly distributed, not orbiting around the nucleus. And then they were not able to explain why the atom was stable. Then Bohr gave his model where he showed that this is an orbit, it is going around it like this in an orbit, and there were different orbits with different energies. And he was able to explain the hydrogen atom spectrum, because in the hydrogen atom spectrum, remember that was the puzzling thing, that why the energy was not continuously absorbed, why only certain energies were absorbed. He said that there were different orbits, and the one which was closest to the nucleus had the smallest energy. The electron, when it went to the higher energy orbit, it would gain energy, and if it was in a higher energy orbit, it would emit energy, but only corresponding to the difference between the higher energy level and the lower energy level. So this is how an orbiting atom. And now we have the wave model where we are talking about probabilities. It is not that there is an orbit or anything. This is an orbital, that where we are only talking in terms of probabilities. The probabilities are maximum inside at some particular position, and they are all the time changing. We can only talk about probabilities as a function of time. So this is the wave model. Today's atomic model is based on the principles of wave mechanics. We've already done a lot of this. What you have to think is that every particle also has a wave associated with it, and if it has a wave associated with it, what a wave is. You've seen, if you throw a stone in a pond, पानी में अगर पत्थर फेंकते हो तो they start going out and they go up and down, so that is a wave. Similar to that, every matter, everything in matter also has a wave character. Now all these wave they do not move about in a definite path. There is no definite path, is the orbit. There is no orbit. You can only talk about when you talk about the planets and the sun, then you can talk about an orbit, because you are talking about very large very large planets. But when you are talking about an atom, then you are talking about very small. What the wave model told us is that it is impossible to determine the exact location of an electron. You can only talk about the probability. You can say that there is an atom, it has a small positively charged nucleus, and there are electrons which neutralize the number of protons that are there in the nucleus, so that it is electrically neutral, but you cannot talk about the exact position of an electron, because it has wave character. So if it has wave character, it has a wave function. And what does the wave function tell you? The square of it gives us the probability. I think we've done a lot of this. And the electron cloud that is found, it is like a cloud, like what you find. What is an electron cloud? Like badal, it is space in which electrons are likely to be found. You find out the probability, and where you make a circle where 90% probability is there that the atom is the electron is definitely going to be here, but the probability is never zero. think like this, when you talk about classical matters, if I say this laptop is on this table, so I am sure that it will not fall down. Classically, this is what I'll think, and this is how we all think. But suppose this was a quantum laptop and this was a quantum table, there would be some probability of this laptop falling through the table onto the floor. And this is how it happens with electrons, that even if there is a barrier, koi rukavat between the electron and the outside world, the electron is able to go through that and think like that. I mean, instead of doing a lot of quantum mechanics that you can find in books and you can try to, I want you to get the philosophy about quantum mechanics, how to think, otherwise you will be shocked by whatever answers you get. Okay? Electrons whirl about the nucleus billions of times in 1 second. They are not moving around in random patterns. Location of electrons depends on how much energy the electron has. If zyada energy hai, तो it can go far away from the nucleus. If the energy is less, it cannot go far away from the nucleus. And depending upon their energy, they may be in a higher energy orbit. In that case, they will be further away from the nucleus. There will be more probability at a larger distance from the nucleus, and those which have the lowest energy are closest around the nucleus, because remember, electrons are negatively charged and the nucleus is positively charged, so there will be an attraction between them, so it will try to be close to the nucleus. Those with the highest energy are found in the outermost energy levels, far from the nucleus. So this is what we have up till now. The Greeks, that is Democritus and so on, they thought that the atom was indivisible, usko break nahi kiya ja sakta. Dalton also thought like that, but once the electron was discovered by Thomson, then they realized कि नहीं ऐसे नहीं है, the electron can be removed from an atom. So Rutherford also believed that, Bohr also believed that, and today's wave mechanics also believes that. Nucleus was discovered by Rutherford because he realized कि वो repulsion between a positively charged nucleus and the alpha particle. So after that, this was accepted. See, what is a model? कुछ हम सोचते हैं, whenever we get more results, so we keep on changing our model. So this is how our model changed. Bohr brought in the orbit, but today we do not talk about orbits. We talk about an electron cloud or an orbital. So this is how I would show you a 1s electron as a probability density, but you see there is more concentration in the middle, so I could draw a circle. It looks like a sphere, like a ball or something. We could draw a circle where most of the blue points are there to show that most of the time, 90% of the time is the electron is going to be here. But you cannot say that the electron, even if you have an atom somewhere here in Delhi, its electron cloud could also be in New York, because quantum mechanics tells you that you can the electron cloud could be anywhere. Today they are talking about in metaphysical terms about quantum mechanics, because you can affect what is happening very far off using quantum mechanics. So I am now coming to what actually you people were asking, many of you were asking, and orbitals and quantum numbers. Now, as I said, out of the atoms, the only atom that can be solved exactly is the hydrogen atom. Although you can solve it exactly, the solution is quite difficult, and we teach it at the postgraduate level. We don't even teach it at the graduate level. But I'll try to explain in simple terms how the solution is obtained. Now, since the atom has spherical symmetry, it's like a ball. So instead of working in Cartesian coordinates क्या है? X, Y and Z. For a box kind of thing, they are very good to use, क्योंकि a box has 3 dimensions like this. But when you are talking about a circular object, then it is better to use something like spherical polar coordinates, which are similar to that, but they have, instead of X, Y, Z, you have R, theta and phi. Simply said, I will say this: R is the distance of the electron from the nucleus. So theta is it, and phi give the orientation. They are angles. Theta can vary between 0 and pi, that is 180 degrees, and phi can vary between 0 and 2 pi. I will not bother you with that. You can look up, if you've studied maths, you will see what spherical polar coordinates are all about. Now once you do that, you get a solution for the hydrogen atom, and we first separate it into the phi part, the theta part and the r part. The phi part gives us one quantum number, theta part gives us another quantum number, and r part gives us another quantum number. Beginning with r, I tell you that there is a principal quantum number which is called n. This is the same as the Bohr's n. Bohr, if you remember, said that there were orbits that the electron could take around the nucleus, and he numbered them as n is equal to 1 was the one closest to the nucleus. That means the lowest energy, n is equal to 2, and all of them had negative energy. Think like that also. The energy of the electron in an atom cannot be positive, because if it were positive it would lose that energy and the atom would break. This doesn't happen. So what is happening is that the energy of the electron is negative. It is most negative around the when n is equal to 1, when it is closest to the nucleus, and as n becomes larger, the atom becomes larger, because now it can go further away from the nucleus, it has higher energy, it is not so attracted. The only potential energy that an electron in an atom can have is the attraction to the nucleus. There is one electron, you know that opposite charges attract, so the nucleus and the electron are attracted to each other with a force which is the Coulomb force, which varies as the potential energy varies as 1 by r minus z by r, where z is the atomic number. So if we solve this, you find that there is a principal quantum number, and according to the kind of solution you get, n can take on values starting from 1, 2, 3 and so on, but not values like 1.2 and 1.3 or anything. It has to be an integer, it has to be a whole number, a number without a decimal point. The second quantum number that you get from a solution for the theta part of the solution is the azimuthal quantum number L, which can take on values like up to n minus 1. So if n is equal to 1, L can only have a value equal to 0, but if n is equal to 2, in that case L can have values 0 and 1. Now actually, because of spectroscopy, there were sharp, principal, diffuse and so on. These were labeled as S, P, D, F. L is equal to 0 and is equal to S. When L is equal to 1, it is called a p orbital. When L is equal to 2, it is a d orbital, and 3 it is F, and so on, G, H, I, J, K and so on. But we never come across anything beyond F from the known elements. You know that only 100 odd elements are known right now, so we do not reach that level. Magnetic quantum number again depends upon the orientation of the angular momentum. L tells us about the angular momentum, the magnitude, the amount of the angular momentum, where M tells us that even its direction is quantized. It can only take on certain values, where ml is a quantum number which can take on values from minus L to plus L. It gives you the 3D orientation of the each orbital. So these are the wave functions that have been solved. You will find them in books. I have taken this from Wikipedia. You can get them from anywhere. You find that the s orbital, n is equal to 1, L is equal to 0, m can only take on a value of 0. This is an s orbital, and it is a 1s orbital, because n is equal to 1, it is 1s. When n is equal to 2, it becomes 2s. L is equal to 0, so it is s. When n is equal to 0, m can only take on one value. So there is only one wave function, and this is given by this. You find that it is exponential minus rho r. Now this rho, that is the distance from the nucleus divided by a naught, which is actually the most probable distance from the nucleus. We will skip all that, but see that it is an exponential function. Now if you plot this function, look at the function on the left. The function on the left is an exponential function. If you've studied maths, if you plot this exponential function as a function of r, it is an exponentially decaying function. What is the property of this exponential function? Only when rho becomes equal to infinity, will it become to zero? That means only at an infinite distance it becomes equal to 0, but at some particular distance it almost becomes equal to 0. It never becomes equal to 0. This is what I said, the wave function of that 1s electron will remain there even at an infinite distance, even in New York, anywhere, North Pole, anywhere you go, that wave function will remain there.
We'll be discussing about these wave functions more. Before that, we have a caller from Uttar Pradesh. Hello.
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 Yes, ma'am. My question is that from where the atom gets energy to revolve?
From where does atom get energy to revolve?
It doesn't, actually, again I am saying it doesn't revolve. This is a wave function. See, there is no orbit. Bohr's model was wrong. It doesn't revolve around the nucleus. It is not a particle. I am stressing again and again. It is not a particle. It is a wave. It doesn't revolve around the nucleus. उसकी energy आती है from the attraction to the nucleus. It is negatively charged and the nucleus is positively charged, but it has a wave function. Look at the graphic now. What we have plotted is the probability on a 2D contour. Please show the slide.
Please show the slide.
Yeah, you see on the left hand side, I have shown the slide, in the slide, the probability distribution. It is like, you know, when तीर चलाते हो तो there is one where you keep on striking. So most of, if you are good, most of those arrows will strike the center. It is like that. At the center you have more probability. The probability never becomes 0, but at some particular point वो काफ़ी कम हो जाती है. You are seeing that you don't see any orange lines beyond a certain point. जो ऊपर वाले I have shown exponential curve where it becomes almost 0. ठीक है. Please don't think about the electron as a particle orbiting around the nucleus. This is exactly the point I want to make, that in wave mechanics it is a wave, not a particle. ठीक है. There we talk about probability densities. Now when you go to 2s orbital, do you see the graphic on the right? There is a point in between where the probability becomes equal to 0, because there is a 2 minus rho. So when rho becomes equal to 0, the probability becomes equal to 0. When you plot the probability densities, you see a white circle, and this is the point where the probability is equal to 0. Again, it is not, you know, just a particular radius. It is a very thick slice where it is equal to 0. Now this is called a node, where the wave function becomes equal to node. When you go to the 3s orbital, you find that there are 2 nodes. In fact, the number of nodes in an s orbital is equal to n minus 1. So 1s has no node because n is equal to 1, 2s n is equal to 2, it has 1 node, n is equal to 3, it has 2 nodes, and n is equal to 4, 4s will have 3 nodes, so on. So as this is again a fundamental principle of quantum mechanics, that as the number of nodes increases, the energy also increases. So the ones with the larger number of nodes have larger energy. Sorry. So this is how we represent the orbitals. All the s orbitals are spherical. They are orbitals, not orbits. The electron is not revolving around the nucleus. We can only talk about where the probability is maximum, and if we plot that, we find that it looks like a sphere. So we say that all the s orbitals are spherical. As the n increases, the s orbitals get larger. As n increases, the number of nodes increases, and that means the energy also increases. A node is a region in space where the probability of finding an electron is 0. So, and that is why you are localizing it. Usko, you know, at that particular point it cannot exist. At a node, the wave function is 0, so its probability is also equal to 0. And for an s orbital, the number of nodes is equal to n minus 1. I have already told you all these things. And now look at, here I am showing the slices. We are showing a slice. You see the white circles. It is 3-dimensional. जैसे it's like a watermelon, तरबूज लेते हो, उसको काटते हो, तो you see what it looks like. It is something like that. Or inside you see a white point where the probability is 0. In the center the probability is more, so you have dark blue, and very far off the probability keeps on decreasing. हमने सिर्फ plot किया है contour where the probability after that is very small, so we can ignore it. And you see 1s is smaller, 2s is larger, 1s does not have any node, 2s has one node, 3s has another node. Now when you come to p orbitals, what are p orbitals? When L is equal to 1. You cannot have a p orbital when n is equal to 1 because L can only take on a value equal to n minus 1. So अगर n is equal to 1, L is equal to 0, you can only have an s orbital, and that is the 1s orbital. When n is equal to 2, then you can have L equal to 0 or 1 because the maximum value of L can only be n minus 1. So you can have an s orbital. I have already shown you the 2s orbital. There will also be 3 p orbitals. Why 3? Because when L is equal to 1, ML can take on values plus 1, 0 and minus 1. We call them as px, py and pz because one of them is oriented around the x axis, one along the y axis and one along the z axis. Now the orbitals are dumbbell shaped. When you go to the gym, you find that there are two balls and connected with a rod. It is something like that. I'll show you just now. As n increases, the p orbitals get larger, same as s orbitals, and they all have a node at the nucleus. Look at this. This is the on the left. We have plotted the probability. We find it looks like this, and so we show the shape of the orbitals must be like this by drawing full lines. And you see at the origin there is 0 probability in all the 3, and they are oriented in the 3 Cartesian directions. Now similarly you can do it for the d end of orbitals. Again n is equal to 2 cannot have d because L cannot be equal to 2, but when n is equal to 3, L can have 0, 1, 2 values. You can have a 3s orbital, you can have a 3p orbitals and 5 3d orbitals, because when L is equal to 2, M can take on 5 values plus 2, plus 1, 0, minus 1, minus 2. So I will show you these. 2 of the d orbitals lie in a plane aligned along the x, y and z. 4 of the d orbitals have 4 lobes each, and 1 d orbital has 2 lobes and a collar. This is how they look like, and these have been plotted again by plotting the electron density, and this is what they look like. And one of them has a collar, the one at the bottom right hand side, it is called the dz square orbital. Then you have dx square minus y square, dxy, dyx and so on. So now I'll briefly, in whatever time we have, I will talk about the applications of quantum mechanics so that you understand how in almost everything in everyday life quantum mechanics makes a contribution, and why you must study quantum mechanics if you actually want to do any kind of research in any of the sciences. One is in NMR spectroscopy. Now NMR spectroscopy and quantum mechanics are intimately related, क्योंकि what you study in quantum mechanics is very theoretical. You will solve some differential equations, get some results. How will you verify that what you have done is correct or not? How will you verify that? You will verify that by doing a spectroscopic determination. Now how do you do a spectroscopic? I told you one of these is that you allow light to pass through light. There are different regions in the electromagnetic spectrum. You can allow it to fall on the particular molecule that you are studying, and then see the radiation that comes out. So wherever there is absorption, the intensity of the radiation that comes out will be less because some of it has been absorbed. That tells us that this energy corresponds to 2 different energy levels. Now in NMR spectroscopy, you look at the hydrogen atom. I'll just come to that. Scanning tunneling microscope has become very important because you will say that I've talked about the atom and all this was very theoretical. How do we know that all this is there? Today with STMs, the scanning tunneling microscope, you are able to see the atom. You can see its wave function. Maybe in some future talk I'll show you the kind of wave functions that you can see on an atom, how you can see the atoms. And quantum cryptography is like codes. Suppose today I think in one of the lectures I did say that today you send information on the internet and it has to be safe, because otherwise people should not be able to read. In quantum cryptography, what happens is that the information you send, if somebody wants to eavesdrop, कोई सुन रहा है, so you will come to know because the message will change. Interesting. Quantum computation is going to be a reality where your computers will become so small, and that means, I mean, I'm not talking about it being small, but they will become, in the same size, they will have much more that you will be able to do with the quantum.
I think we have a caller with us. Hello.
Good morning, afternoon, ma'am.
This is a call from Madhya
I
Pradesh. Please
have a
ask your
theory
question.
about one question.
Hello?
Good afternoon, ma'am.
Yeah.
Ma'am, de-wedding model and Bose model, what is the difference in it?
It is a request to you, please अपने जो आपका टेलीविजन है उसकी वॉल्यूम थोड़ी कम कर दें, आपकी आवाज़ इको कर रही है.
De-wedding model and Bose model, what is the difference in it?
Bose model and whose model?
जी.
Which model are you talking about?
One is Bose model and the other one क्या है? Hello?
De-wedding model.
D?
De-wedding model.
De Broglie?
I think
De-wedding model.
Debye?
de Broglie's model. I think
Debye had nothing to do with atomic. It was to do with electrochemistry. Bohr model is about an atom. Bohr model, he postulated that क्योंकि they were not able to explain why the atom is stable. So what he said was कि एक nucleus है, उसके around there are orbits. उन orbits में अगर electron है तो stable होगा. And how do you know these orbits? Because angular momentum is quantized in these orbitals. It can take on only certain values. He was able to explain the stability. But today, I mean, what I'm talking about is quantum mechanics. That was not quantum mechanics, that was semi-quantum. But पहली बार he talked about quantization, so we call it quantum. Today we follow the wave model where we say there are no orbits, there are orbitals. अगर आप Debye-Hückel कह रहे हैं तो Debye-Hückel was something to do with electrochemistry, which has nothing to do with this. Both of them did not talk about this. अगर de Broglie कह रहे हो तो de Broglie said कि matter also has waves. ठीक है, क्योंकि अगर वो particle है electrons.
Sorry to interrupt you, ma'am. There is another caller with us. Hello.
Good afternoon, ma'am.
Yes, this call is again from Madhya Pradesh.
Ma'am,
Please ask your question.
I want to ask how the 3D orientation takes place in the models. I am calling from Dr. Hari Singh Ghosh, Central University, Sagar. My name is Gaurav Mehgai.
Yeah. You are talking about the 3D model. I said ना इसको अगर solve करते हैं hydrogen atom we are able to solve completely. ठीक है? So then we plot the probability density. हम हर point पे we have the wave function. ठीक है, wave functions मैंने वो लिख के दिए थे. तो those wave functions अगर आप plot करते हो at different values of r, different values of theta, they depend upon r, theta and phi. तो अगर हम वो plot करते हैं, what we do get is कि probability जो मतलब स्क्वायर ऑफ दैट वेव फंक्शन हम प्लॉट करते हैं, किस किस पॉइंट पे कितनी प्रोबेबिलिटी है, वी फाइंड कि इस टाइप की शेप आ जाती है. यू अंडरस्टैंड? मतलब d orbitals have to be 5, that we know because from the conditions of the solution of hydrogen atom कि n has some value, l can only have a value up to n minus 1, all the values up to n minus 1 starting from 0, n can have 2n plus 1 values. So when l is equal to 2, there are 5 d orbitals, और by plotting the probability densities उसका बड़ा hazy सी picture आएगी which we just make into a
I hope the caller might have got his answer. We have very less time left with us, ma'am. Please sum up with this lecture.
Yeah. So finally, what I was trying to convey to you people was that the quantum mechanics is based on a few postulates, and these postulates tell you how to go about a quantum mechanical calculation. So suppose you have the hydrogen atom that you want to solve, because we are working on the hydrogen atom. You will write down the classical expression for the energy, convert it into a quantum mechanical expression, get the eigen functions and eigen values, try to interpret everything, and then you can find many other properties of the hydrogen atom.
This very topic is in itself is a huge and immense subject to learn about, and we hope Professor Kakkad would be coming in future lectures also, and will be solving your queries and giving more insight into this very topic. Thank you, ma'am. Thank you so very much for being with us.